Hello, welcome to this MATLAB video tutorial. In the previous video, we introduced the bisection and Newton methods to find the roots of a function. Today's lecture is concerned with the second method, but also with the convergence criteria for all these methods. So when do we want to stop? When can we guarantee that the solution is an enough good approximation? And finally, we will also look at the convergence graphs. So let's get started. Let me introduce the basics of the second method. When we introduced a Newton method, the idea was that given an iteration xk plus 1, we want to compute the next approximation, and the idea of Newton method is to compute it as the zero of the tangent line to the function through the point xk plus 1. So if we look to the graph here, we have xk plus 1, we evaluate the function at that point, and we compute this green line is the tangent line to the function. It's tangent to the blue curve, which is f of x. And this tangent line, we can compute it 0. That's very easy, it's line. Yeah? So we can compute xk plus 2. That's going to be our next approximation with Newton's method. So what's the difference with the second method? The second method, instead of computing a tangent line, it will compute a line through two different points. So it will use xk and xk plus 1 as initial points, and it will compute the second line through these 2 points, okay? So this red line is a second line through these points, and the zero of this line is going to be the next approximation with the second method. Okay, so the main idea here is instead of using a tangent line that involves the derivative of the function, we will use a second line that will not need to know the derivative. That can be understood better here if we look to the formulas of the methods. For the Newton method, the formula looks like this. Remember that we had here in the denominator the derivative of the function, because that's the slope of the tangent line through that point xk plus 1. Yeah? Now, with the second method, the idea is instead of using the slope of the tangent line, we will use the slope of the second line. We compute this way. Yeah? So we are avoiding the use of the derivative of the function. Okay? So that's the main idea of the second method. So now I want to illustrate how it works in MATLAB. So first of all, when we start MATLAB, we must define the working directory, our current folder. For me today, I will work in this folder, and I want to illustrate how the second method works. So I will edit this file, main illustration of the second method. Here I will define two initial points. That's similar to bisection method. Yeah, it uses two initial points. So the same is going to happen with the second method, because we need to construct the line through second line through two different points. So we need two initial points. Then we will define the function we want to find the zeros, and here we will plot the function just to see how it looks like. So let me just write this part of the code. So this is the function we want to find the zero. We can see here it's very easy in this case. We have a 0 at 0.9. Yeah. So just to illustrate how the second method works, here I will initialize this vector called results with the first initial points that we define. Okay? Now the first iteration of the second method is the following one. We initialize these variables xk and xk1, it stands for xk plus 1, let's say, yeah, with x0 and x1. Then we compute the slope of the second line using the formula we saw before, and then we compute xk plus 2. using again the formula we saw before. Now in the denominator we don't have the derivative of the function but the slope of the second line. So if we do that, then we can plot these points xk, xk1 and xk2 and see how it looks like. So we can see here how we use these 2 points to compute the green second line through them. So xk2 is the 0 of this line. So the main idea now is to iterate. We know these are iterative methods. So the idea now is that xk1 now should be called xk, xk2 should be called xk1, and we will do another iteration to find the next point. Yeah? So here we have this update. We have to update the variables. We will assign to xk the value of xk1. We will assign to xk1 the value of the last computed xk2. So we update these variables and we add to these vector results the last computed iteration. Yeah, so this way the vector results contain the first initial points and the first iteration of the second method, which is 9.3. Okay? Now we would do the second iteration. Yeah? So we again repeat the same. We compute the slope, we compute the next iteration, we plot it, we update the variables, and we add it xk2 to the vector results. Now we can see that this was xk, xk1, so now xk2 is really close to the root. Yeah? So this second method is going to be faster than bisection method for sure if it converges, and not that fast as Newton method, but quite close to it. Okay, this second method is going to be super linear. We will see that afterwards with the convergence graphs. Okay, so this is how the second method works, but we want to code it. Okay, we want to write a function called secant that performs the iterations of the second method. Now, I want to write the code with you, and to do so, I will start from Newton's code. Okay, in the previous video, we saw how to code Newton's method in a function. We had as input variables the initial point, the function, its derivatives, and the number of iterations we want to do of Newton method. And then we coded this Newton method. Now, what I want to do is I want to code the second method from Newton's function. So I want to make some changes here in order to code the second method. So what I should take in mind is all these changes that we need to do. So let me do these changes with you in MATLAB. So maybe it's better to undock the editor. And let's do it together here. Okay. So first thing we want to do is to open Newton's function. So let me open Newton. Now, first thing we want to change is the name of the file and the name of the function. So instead of Newton, this is going to be the second method. So the first thing is to say file, save as, and say that this is going to be the second method. Okay, so I will save as secant. And of course, if the name of the file is secant, then here the name of the function must be secant. Okay, next thing I need to change is that the input variables now are different. Now I have x0 and x1 as input variables, but I don't need the derivative of the function anymore. Okay, so my input variables are x0, x1. the function, and the number of iterations. Okay, so it's a good idea to explain here that now we have two initial seeds. We don't need the derivative of the function. So these are the input variables in this case. Okay, the output variables remain the same because the objective is, of course, to find the root of the function by performing some numerical iterations. Okay, now let's initialize not only xk but also xk1. Remember that with the second method we need two variables, xk and xk1, so we initialize them with the input initial seeds given by the user. Now the vector iterations will contain not only x0 but also x1, so here we need to add x0 but also x1. Okay, now inside the for loop I need to compute the slope of the second line. Okay, so the slope of the second line is going to be f xk1 minus f xk divided by xk1 minus xk. This will compute the slope through these 2 points, xk, xk1, and after that we will apply Secant's method, but only if this slope is not 0. So if in absolute value this slope is greater than, this is like almost machine precision, if it's greater than this, then we will perform the iteration. Otherwise we will say, sorry, but we had an error in the second method, and the problem is that the slope of the tangent line is almost 0. Okay, so I cannot divide by 0. Okay, so in case we want to do the iteration of the second method, the only thing we need to change here is that instead of the slope of the tangent line, we use the slope of the second line. That's it. Yeah? But then the update of the variables must involve not only xk, but also xk1. Yeah? So xk takes the value of xk1, and xk1 takes the value of the last computed iteration, which is xk2. And now, in the vector iterations, we need to update with the new computed iteration, which in this case is, oh sorry, this should be xk2. Okay, xk2 is computed from xk1, f of xk1, and the slope given by the second line. Okay, you can see this formula is the one we used in the slides. Okay, we update the variables, and then here we have to add the last computed iteration, which is xk2. Okay, so that's it. We save it. Let's save it. File, save. And now let's check if it works. Okay, let's do a new script. Oh, what's going on here? Okay, I hope everything is okay. So let's do a new script to illustrate how the method works. I will call it main compare methods. Main compare methods. And the idea here is to call the second method and compare it with Newton and bisection. So let's start with clear all CLC to clear the common window, format long in order to have all the decimals. And let's define a function. For example, we will try to find the zeros of x times log x minus 1. Let's say we want to do 5 iterations, and we will try to call the second method, okay? In order to call the second method, we need 2 initial approximations, x0 and x1. I will choose 1 and 2, for example. And then I need to call the second method. The way to call a function, it's exactly as we define it, but without the word function. So I will just copy and paste here. I will call second method with 2 initial points, an already defined mathematical function, and with 5 iterations. Okay? So if I do that, we can see how it converges to this approximation of the root. You can see that in the last iteration, almost all decimals are the same, so just that this decimal here changed, okay? So we are very close to the exact solution. Now what happens if instead of second method we call a Newton method? Okay, so let's open Newton method. The way to call Newton method is like this. Yeah? So let me try to call Newton method in order to compare. Now here I need to define the derivative of the function. So I will define it here. This is the derivative of this one, which is 1 times log x plus this one times the derivative of the logarithm, which is 1 over x, so the result is 1. Okay, the derivative of a constant is 0, so that's what we get. And now I can call Newton's method. Maybe it's a good idea, if this is exactly the same, to change it. I will call these iterations from the second method, root from the second method. I will call these iterations from Newton, and the root from Newton method. Okay? And finally, we can also compare with bisection method. Let's open bisection. Bisection method. I don't know what's going on here. I hope it's just some graphic problem. Okay, so to run the bisection method, we need to copy like this, and call it like this. Remember, here we need x0 and a, so maybe a could be 2. Okay, x0 is 1, a is going to be 2, function and a number of iterations, and in this case I will call these iterations bisection and root bisection. Okay, so let's run this, and then we can see, for example, that iterations from this bisection method, they get this value. However, with second method, we have a much better convergence. The last 3 iterations are pretty closer to the root, and for Newton method, the convergence is a little bit faster than the second method. Okay, so the idea is that bisection is the slower one, but the most robust. It will always get to an approximated solution. However, Newton and second method may not converge, may not give you a solution, but in case they converge, they can really do it very fast. With Newton, we can have quadratic convergence, and with the second method, what is called superlinear convergence. Okay, so now what we've done up to now is to fix a priori the number of iterations we want to do of any of these methods. Yeah, but what we should do is to use the so-called convergence criteria. So let me show you what are these convergence criteria. So the convergence criteria is that xk satisfies this convergence, this stopping criteria, when the function at this point in absolute value is smaller than a given tolerance that we will call, let's say, tol f, and also the relative error of this point xk is smaller than a given tolerance tol x. Of course, we cannot compute the exact relative error. We would really like to have here the exact value, let's say alpha, yeah? But we don't know alpha, we are looking for alpha. So instead of that, we compute an approximated relative error. What's the best approximation that we have of alpha? The next iteration. So instead of alpha, we are using here xk plus 1. So this is called the approximated relative error. And we say that xk is a sufficiently good approximation when its approximate relative error is smaller than a given tolerance, but also when we know that the value of the function at that point is smaller than tol f. Of course, these values of the tolerances are given by the user, and it depends a lot on the problem you are solving. Okay, so let's explain how we can introduce these convergence criteria in our code. So one way to introduce this convergence criteria is like this. I call this Newton 2 because instead of performing a fixed number of iterations, we have as input variables tol f and tol x, so the tolerances we want to use to stop. The main difference with this function and the previous one we used of Newton is that instead of having a for loop with a fixed number of iterations, we use a while loop with the condition to know if we have to stop or we have to keep on iterating. So we introduced here a logical variable, shall we stop? Initially, shall we stop is no. Remember, logical variable 0 means no. So while shall we stop is no, keep on doing iterations here. But when this logical variable changes to 1, then it will get out of the while loop and finish. Okay, so the main idea here is we need to check whether the convergence criteria are met or not, and it's done in this line. Okay, here we are telling that the logical variable shall we stop is equal to this condition and this condition. So if both of them are satisfied, if the absolute value of f of xk is smaller than tol f, and also the relative error is smaller than tol x, then shall we stop will be yes. So that means it will get out of the while loop. Okay? So the idea is to use this logical variable to decide whether we shall keep on or we should stop. Now, let's test this function. Let's do a new script. I will call it main Newton. Just to check this main Newton 2. And the idea here is, I always need to write this, it's very important, clear all clear the common window, format long, to make sure we display all the decimals. And let's define a function that we want to compute its zeros. So x times log x minus 1, for example. And let's define the tolerances. Maybe I will use 1, okay, to the minus 5, 10 to the minus 5, and I will use tol x just the same as tol f, okay, the same. Now, I would like to call this Newton 2 function, so I'm just going to copy this and paste here. Now, I need an initial point, x0. I don't know, maybe we can use, I don't know, 2. And I need also the derivative of the function. Remember, this is this, okay? And what else? We have the initial point, we have the function, the derivative of the function, and the tolerances. So now we can run this. And that's what we get. It took 1, 2, 3 iterations in order to find an approximation that satisfies the convergence criteria with these tolerances. Okay, so 1, 2, 3, because this one is x0. Yeah. So instead of this tolerance, I use, for example, this one. Of course, it will need more iterations to satisfy the convergence criteria. Yeah, we can check that. Now we will see 1, 2, 3, 4 iterations in order to satisfy this harder criteria. Yeah, more restrictive. Maybe we can use this tolerance and do some debugging just to show you how it works. So let's put a stop point here and run. Now it stops here, so I will do step in to get into the function. Now we initialize xk, initialize the vector iterations, initialize the variable shall we stop. We can see here shall we stop is no, and we define an xk which is 0, and now while shall we stop is 0, keep on. Yeah, so I do a step, I get inside the while loop, I update the vector iterations, and then I do this if this value is greater than let's say 0 machine precision. Let's do an iteration. So I compute xk1, and then I'm asking, shall we stop? Well, in order to know if we shall stop, this condition and this condition both must be satisfied. If I check this condition, it says no, it's not satisfied. The absolute value of f of xk is not smaller than tol f. In fact, we can check that this value, sorry, the parenthesis was missing, is 0.38, so it's much bigger than 10 to the minus 5. Yeah? So we keep on, and we do another iteration. We compute xk1. Now let's check if this condition is satisfied. It's not satisfied. We can see that, again, this value is smaller than before, but still greater than 10 to the minus 5. So we will keep on computing the next iterate. Then we will check this condition. MATLAB always checks the first condition, and if it's not satisfied, it will skip checking the second condition, yeah, because both of them must be satisfied. So if the first one is not, it will just say, okay, this is not satisfied. Yeah? So again, we don't satisfy, so we iterate one more time. Now let's check this condition. Oh yes, now this condition is satisfied. We can see that the absolute value now is 10 to the minus 11. So of course this is smaller than 10 to the minus 5. Now let's check the second condition. Is this second condition also satisfied? Yes, it is also satisfied. So in this case, when I do the step, the variable shall we stop now is yes. It has a 1 here. So when I step, it will get out of the while loop and we will stop. We will step out of the function and we are done. Okay? So this is how a while loop with the stopping convergence criteria works. Now I want to show you this main stop criteria file. Here I'm checking all methods, bisection, Newton, and secant, with the convergence criteria, all of them, and we will see using the same tolerance how do they perform. Okay, if I do this, we can see, for example, with the iterations of the bisection method. They are called, yeah, bisect. Okay, we can see it's quite, there are a lot of iterations here. However, for Newton, we have a few, yeah? So with the same tolerance, bisection method needs a lot of iterations, but Newton just a few iterations. So maybe it's better to see how many exactly iterations they do. We can see here 19 iterations for bisection. In fact, that means 18 because the first is the initial set. For Newton, that means 4 iterations because we have the initial point. And for bisection, for the second method, we have 4 iterations because there are 2 initial points. Yeah. Of course, we can increase this and see what it happens. We see bisection, Newton, secant. So this is bisection, a lot of iterations. Remember, it is very slow. But Newton and secant, they perform similarly. Normally, Newton will do a few more iterations, but you need to know the derivative of the function, compute it, and secant gives you a quite good convergence, which is called superlinear, and you don't need the derivative of the function. Okay? So that's how the methods work. However, I want to explain you how, if I need to compute the zero of a function, what would I do? Well, I would use a built-in function in MATLAB that is called f0. Okay, you can write here help f0 and see what it explains. It's a built-in function in MATLAB that computes the roots of a function. I will just explain here very briefly how it works. The simplest way to use it is, let's say I want to compute the zero of this function I'm going to plot now. Okay, I want to compute the zero of this function. I can visually see that the zero is close to 1, let's say. So I will use the f0 command, and it just needs the function that you want to compute the zero and an initial point. If we run this command, we will get a quite good approximation of the solution. Oh, I see I'm still debugging, sorry. Let me quit. Okay. So this is how we use it, but there are options we can activate to get more information of how it works. So let me run again the command, but with these options. Please display the iterations you are doing. And here we can see that the f0 function starts trying to find an interval where the sign changes. So I gave as an initial point 1. So it checked the value of the function is negative there. Yeah, that was my initial interval, 1, 1. So in fact, it's the point. So I decided to move a little bit to the left of 1 and check the sign of the function, and move a little bit to the right and check the value of the function. Both were still negative, so it moved a little bit to the left, a little bit to the right, check again the signs, and so on. And finally, it found a point where at the left side of 1, which the function is negative, but a point 1.16 where the function is positive. So finally, it could find an interval 0.84, 1.16 where the function changed sign. This is the idea of bisection method, yeah, to work in an interval where the function changed sign. And then it tries to search for a 0 in that interval, in this interval where the function is changing sign. Yeah? Now I'm not going to explain exactly which method is this one. It's similar to Newton's method. Okay, it has quadratic convergence, and the idea of the F0 command is that it is an hybrid method. It somehow uses the idea of bisection method to find an interval with the change of sign of the function, but also uses a method close to Newton method to have this very fast convergence to the solution and to get a lot of precision in the solution with very few iterations. Okay, so that's how F0 function works. It's very important that you can also play with tall x and tall f with this F0 command. So the way to do that is to call the F0 function with tall x. This is telling this command to use as tall x 10 to the minus 6 and to use as tall f 10 to the minus 6. So these are exactly the tolerances we used before. So we can call the F0 command with different tolerances. So it will need few iterations, but of course the solution will be less precise because now the tolerances are not machine precision, but only 10 to the minus 6. Okay? So this is how the F0 function works. So now let's move to the last part of the video where I want to show you the convergence graphs. Convergence graphs. What we do in convergence graphs is to plot the error of the methods. So let me show you what we do. First, we define a function, its derivative, initial points to use for the different methods, the tolerances we want to use, and then I call the three methods we are working with: bisection, Newton, and secant. After doing that, I will have three vectors called iterations from bisection, iterations from Newton, and iterations from the secant. What I'm going to do with this is I'm going to compute the almost exact relative error for each of these iterations. The relative error is the exact value alpha minus the iteration divided by alpha. Here, the way I compute the almost exact value of alpha is using the F0 command with machine precision. So the tolerances here are 10 to the minus 16. And here I compute the error. So let me show you, if I do this, these vectors, error bisection, error Newton, and error secant, contains the error of each of the iterations. Yeah? So now I can compute the convergence graphs. The convergence graphs plot in the x-axis the number of the iteration, and in the y-axis the logarithm of the relative error at that iteration. So here we are plotting in the x just the vector from 1 to the length of the iterations we have. So this is 1, 2, 3, 4, and so on. And here the logarithm of the error for each of the three methods: bisection, Newton, and secant. So if I do this, we can see how bisection method is the slower one. It has this linear convergence. Newton, which is the green line, is the faster. These are iterations, yes? So just with 5 iterations, it gets the most precision of the 3 methods. Second method is in between, but it's closer to Newton, yeah? So it's also a fast convergence method, but it doesn't need the derivative of the function. So it's a nice method to bear in mind. Yeah? So this is how convergence graphs work. That's everything I wanted to cover today. So see you in the next lecture. Bye-bye.